Hi there, I'm Alan Viggen from the Norwegian University of Science and Technology, and I'm going to give you a brief overview of some work on subsonic radiation that I've done together with Håvard Arnestad from the University of Oslo. First of all, let's look at the classical radiation model, where the case is that we have a surface vibration moving at a particular speed, and this is generating a sound wave in an adjacent fluid. Now, this gives us two domains. In the supersonic domain, the surface vibration is moving faster than the speed of sound in the fluid. We get an outgoing wave being radiated by the surface vibration. In the subsonic domain, on the other hand, the surface vibration moves slower than the speed of sound in the fluid. We get an evanescent wave that clings to the surface, which means that as we go away from the surface, the amplitude decreases exponentially. Now, this classical model has some deficiencies. One is that it disagrees with some exact guided wave results that have been found in the literature over the last 30 years, where they show that you can actually have subsonic radiation in the subsonic domain, which means that even if the vibration is slower than the speed of sound in the fluid, you can still have energy being radiated out into the fluid. Now, these papers follow a mathematical approach that doesn't give much intuition, and so they can't fully explain why this happens. And furthermore, this classical model, it ignores energy conservation, which means that as the sound wave is radiating power away, the vibration doesn't seem to lose any power, it doesn't get any weaker. So we can look at that first. What happens if we consider the vibration to be attenuated? And here we can compare an unattenuated and attenuated surface vibration together and look at their pressure field. And we see that for the attenuated surface vibration, the pressure wave becomes inhomogeneous, which means that as we move along the wavefront, the amplitude actually changes. Now we can look at the radiation. We can reduce the attenuation a bit to make things a bit more clear. And we can go from the supersonic domain down towards the subsonic domain. And as we near the transition between the two, which is called coincidence, we see this jump in the unattenuated surface vibrations pressure field as it goes from the supersonic domain to the subsonic domain, where the pressure wave becomes evanescent. Now, this doesn't actually happen for the attenuated surface vibration. It still gives us an outgoing pressure wave, no matter how far into the subsonic domain we go. Now, for the next step, we can derive a radiation model, and we do this by considering the balance in energy between the radiated energy, the radiated power, which is radiated into the fluid, and the loss in power of the underlying guided wave, which is underlying the surface vibration. And as we follow this, we can derive a radiation model equation, which is an implicit equation relating the attenuation and propagation of the surface wave. And it lets us also consider the inhomogeneity of the radiated wave. We've also validated this against leak A0 Lamb waves. But we can look at what this gives us. We can see that in the supersonic domain, we have a radiating model that corresponds quite well to the classical model's prediction. But this radiating mode, it actually proceeds into the subsonic domain, unlike the classical mode, which just becomes evanescent as soon as we hit the subsonic domain. Now, in conclusion, it's fairly straightforward to derive a better radiation model. It's been validated against leak A0 Lamb waves, and we can use this to explain subsonic radiation. Of course, there's a lot more to this, and you can find some more details on the poster and also in an upcoming article that is coming in the near future. Thank you very much for listening.